Let's now take a look at the second term in the weak form. That's this term over here, and it involves the derivative of the weighting function as well as the temperature. So my temperature variation is that, and the corresponding variation of the derivative of the temperature is that. And since we have a linear interpolation, the derivative is constant over each element. For instance, if I want to know what is this value, the derivative over here, it's just going to be, this value minus this value divided by the length of the element. So that value is going to be T2 minus T1 divided by delta x, correspondingly for this element and so on. And that's the derivative of the weighting function, and again that's going to be piecewise constant. For instance, this value here is going to be W2 minus W1 divided by that distance, which is delta x. And then I'll have to go and figure out what it is for the second element and so on. And then I need to plug these variations in here, and let's say I'm doing it over the first element. This is constant, and k is constant, so I can bring all of this out of the derivative of the integral, and I'll just get integral of dx over the element, which is the length of the element. And this, so I have to multiply this by this, and w1 is going to multiply t2. It's also going to multiply t1, so I'm going to get terms such as w2 or w1 t1 and w1 t2. Similarly for w2, as I've talked about before. And when you look at the the stiffness matrix form of it, what this means is these terms will go into appropriate rows and columns of the stiffness matrix. So you have to do the bookkeeping, like, okay, this term, I know that it's going to go into the first row of the, whatever coefficient I have here will go into the first row of the stiffness matrix. Which means that this term affects the stiffness matrix, whereas these two terms affect the force vector on the right-hand side. And there's a very important takeaway from this, which is if I want to know the algebraic equation at this particular node, which temperature values will it involve? I'll say, okay, it's going to involve, so I look at what all W2 is multiplying. W2 is multiplying T1, it's multiplying T2, that comes from integral over the first element, and then W2 will multiply T2 in this integral, but it'll also multiply T3. Which means that when I write the algebraic equation, when I collect terms, the algebraic equation at this node will involve the temperature value here, and it'll involve the temperature value here, and the temperature value here. It won't involve the temperature value here. And we can come up with a general principle. So we look at, okay, the algebraic equation here will involve this node, and then we will temperature at this node, and then we will look at the elements that are connected to that node. So I have this element connected to the node and this element, and then I look at what are the nodes connected to that element. So I have this node here that's connected to that element, and this node here that's connected to that element. And I can deduce that the algebraic equation at this node will involve these three temperatures. And I can generalize this. So I have this complicated mesh analysis, and I'm thinking about, okay, this node is connected to these elements, and then those elements in turn are connected to these nodes, and so I know this node, ANSYS will write relationships connecting the temperature at that node or displacement when we go to structural mechanics to all the corresponding nodes. And I feel like that's very useful when I'm in ANSYS.